everyone, I'm Savindra, a sophomore student majoring in civil engineering, and in this video, I will be presenting about line integrals. So line integrals is within the chapter 16, which is the integration in vector fields, and line integral is the first subchapter. Within this chapter, I will cover about the definition, how to evaluate line integrals, additivity, mass, and moment calculations, and line integrals in the plane. So first of all, what is line integrals? Line integrals are used to find the work done by a force in moving an object along a path and to find the mass of a curved wire with variable density. So in this chapter, we extend the theory of integration to curves and surfaces in space. As we know before, if we wanted to find an area below a curve, we can just integral the function itself. But for line integrals, it's used to find the work done by a force in the line itself. So suppose that f of x, y, and z is a real-valued function we wish to integrate over the curve C lying within the domain of f and parameterized by equation O of t equal to g of ti plus h of tj plus k of tk within the range that we set. We need to integrate over a curve C rather than over an interval of a and b. So we get this general integral, which is called the line integral. And the equation below looks similar to the Riemann sum, and depending on how you pick the path for curve C, the result or value that you receive may differ. So to sum up the definition, if f is defined on a curve C given parametrically by equation O of t equal to g of ti plus h of tj plus k of tk within the range set, then the line integral of f over c is the integration of c on the function at a point x, y, and z ds equal to the limit as n approach infinity with the sum from k equal 1 to n of function at the point x of k, y of k, and z of k times delta sk, provided that this limit exists. And we know that the s over dt equal to norm of v equal to the square root of dx over dt squared plus dy over dt squared plus dz over dt squared. So from that, we can plug it in back into the old equation, which was the integration of c of the function at point x, y, and z ds. We turn it into a new integration, which is integration of a to b of the function at point gt, ht, and k of t multiplied by the norm of v of t dt. So how do you evaluate line integrals? To evaluate line integrals, you have to follow these two important steps. First is to find a smooth parameterization of c, which is the given equation highlighted by the blue color, which is the O of t equal to g of ti plus h of tj plus k of tk at the range set that we set. The next step is to evaluate the integral when you found the parameterization of c with your range set. From that, we can turn it into the integral of point a to b of the function g of t, h of t, and k of t multiplied by norm of vt dt. So to further improve our understanding, we should practice an exercise. So to further improve our understanding, we should practice an exercise. So evaluate the integral of c of function x plus y, xy plus y plus z ds along the curve or t equal to 2ti plus tj plus 2 minus 2tk with the range of t larger or equal to 0 and smaller or equal to 1. So first step, we have to parameterize the equation. So we have given the equation, and once we parameterize it, first we have to find the O and dt first. From the equation, we can find the O and dt, which is 2i plus j minus 2k. And norm of di over dt is the square root of this equation, value in the equation, which is 2, 1, and negative 2. We square root those values and we get the result, which is 3. Next, we plug those values back into the initial function within the integration right here. We can then integrate the function. The function that we have to integrate is this one, integral from 0 to 1 of the function 2t squared minus t plus 2 multiplied by 3 dt. So once you integrate this, you plug the value into the integrated products and you will get the answer, which is 13/2. Moving on to the next point, which is additivity of the line integral. So if a piecewise smooth curve C is made by joining a finite number of curves, let's say C1, C2, or Cn to n, we can integrate the function over C, which is the sum of integrals over the curves that it makes up with. The formula is integral of C of the function ds equal to an integral of C at the curve number 1 plus integral of the curve number 2 and so on. But do note that the value of the line integral along a path joining 2 points can change if you change the path between them. So again, to test our understanding, we should practice an exercise. The problem is the graph shows another path from the origin to the point that's set, and the union of line segments of C1 and C2 we then need to integrate the function at the point x, y, and z, which is the equation that is x minus 3y squared plus z over C1 union of C2. And we have given the graph right here. So let's start by parameterizing the curve number 1. We get this function right here with the value that we set, and we have to find the norm of v, which is the ds over dt. We then get the value, which is square root of 2. Next, again, we parameterize the curve number 2. We use the equation with the range that we set as the equation above. We find the norm of v, which is 1. So if norm of v is 1, which it means that ds equal to dt. Next, we can start by doing the integration. So with the formula that I mentioned earlier, the integration with the 2 lines can be added. So integration at curve 1 plus integration of curve 2. So curve 1 and curve 2 have starting and end at the same parameterized point, which is 0 and 1. We plug the value of for each function into its initial function. We get the integral right here. So plugging the values back in, we get the integrate. We get the equation we have to integrate. So this integral, we get t minus 3t squared multiplied by square root of 2 plus the integral of 0 to 1 of the equation 1 minus 3 plus t multiplied by 1. We get the answer, which is minus square root of 2 over 2 minus 3 over 2. Next part, which is the mass. So next part, which is the mass and moment calculations. It is said that we treat coil springs and wire as mass distributed along a smooth curve in space. So when a curve C is parameterized by the equation that we mentioned, O of t equal to x of ti plus y of tj plus c of tk, with the range that we set, which is t larger or equal to a and smaller or equal to b, then point x, y, and z are functions of the parameter t. The density is the function of density of the point xt, yt, and zt. And the arc length is given by ds equal to the square root of dx over dt squared plus dy over dt squared plus dz over dt squared dt. And let's say we pick a formula. So formula of mass is m equal to square root of c of the density ds. We change the density into the equation, and we switch the s to the this square root equation right here. So for mass and moment calculations, there are a couple of formulas that you have to keep in mind. So there's this equation for mass, equation for first moment about the coordinate planes, which is these 3 coordinate of the center of mass, which is x bar equal to m of yz over m, y bar equal to m of the plane xz over m, and z bar is the m or moment of the plane of x and y over m. And next is moments of inertia about axis and other lines, which is these equations right here. And do note that this symbol means density of the point x, y, and z, and this right here means the distance from the point x, y, and z to line L. Again, let's practice on an exercise. So a slender metal arc denser at the bottom than top lies along the semicircle, which is the equation y squared plus z squared equal to 1. As z is larger or equal to 0 in the yz plane, we have to find the center of the arc mass. If the density at the point x, y, and z on the arc is density at the point x, y, and z equal to 2 minus z, and we are given a graph right here. So let's start first. As I said, parameterize the equation. So the parameterized equation is cosine of tj plus sine of tk with the parameter t larger or equal to 0 and smaller or equal to pi. Then we find norm of bt, which is the square root of 0 plus negative sine t squared plus cosine t squared. We get this from the equation in the exercise. The result is equal to 1. Then we can start by using the formula of moment. So the formula of moment is integral of the curve of the density equation, ds. We then use the equation that we were given in the exercise, plug it into density right here. We have 2 dz, 2 minus z ds equal to integration of 0 to pi 2 minus sine t ds, and the result is 2 pi minus 2. Again, using the same procedure on the x and y, on the xy plane, we have to multiply the density by z. So when you multiply that density by z, you will add sine t to the integral, and we have a different answer for that, which is 8 minus pi over 2. And next, to find z bar, or we have to use the value that we found for the m on the xy plane over m, and plugging those values in, we get the result, which is approximately 0.57. So from that, we can conclude that center of mass is at 0.00 and 0.57. So there is an interesting geometric interpretation for the line integrals in the plane. So see this graph. The line integral of the integration of curve C of the function ds gives the area of the portion of the cylindrical surface or wall, which is these parts right here, beneath the point z equal to function at point x and y larger or equal to 0. So from definition, integration of curve of the function ds equal to the limit as n approaches infinity, sum of k equal to 1 to n of the function at point xk and yk multiplied by delta sk, where the delta sk approaches 0 as n approach infinity. We see that the line integral of integration of the curve fds is the line of the wall shown in the figure below right here. And that is all for my presentation. Thank you for paying attention.